Hello, my name is Lei Hou. I'm going to tell you something about vapor bubbles with nanometer size, or nanobubbles, that we generated around gold nanoparticles in liquids and detected optically with nanosecond time resolution. We use a continuous laser at 532 nanometer to hit gold nanospheres and generate nanobubbles, and we probe the nanobubbles by scattering of laser beam at 815 nanometer. The intensity of the scattered probe beam provides information about the dynamics of nanobubble in the nanosecond regime. First, we found that even under continuous heating, nanobubble forms and collapse very rapidly in an inertia-limited process we call explosive. The duration of one bubble is about some tens of nanoseconds. Many cycles of such fast bubble events repeat at a rate of few megahertz as shown here. From the time dependence of this nanobubble instability as shown in this red curve, we propose that liquid layer surrounding the nanosphere first must become overheated. Then the nucleation of a bubble is followed by evaporation of the overheated liquid and expansion of the bubble. The expansion is barely resolved by our detector and appears to be determined by inertia. We therefore propose that this phenomenon is similar to explosive boiling previously observed in microscopic experiments. Second, within a narrow range of heating power, a nanobubble becomes very sensitive to weak local perturbations such as acoustic waves. Here we showed an example of echo-triggered nanobubbles when the heating power is constant but above some critical power. We average a number of these bubble events by taking the half maximal of the red edge and obtain the red curve shown here. Besides the first peak of fast bubble formation and collapse, we can observe a shoulder and sometimes a second peak appearing at well-defined delays after the first peak. We attribute this to the echoes of sound wave released after the first explosion reflected by glass oil interfaces, first between glass slide and immersion oil, second between immersion oil and the front lens of objective. The reflected sound wave can modulate the bubble signal or even trigger a second or third explosion. This observation suggests that the nanobubble could serve as a two-way transducer between optical and acoustic waves and could form the basis of an acoustic radar similar to those working with electromagnetic waves. In summary, we optically generate and probe vapor bubbles with high time resolution on a single particle level. We observe nanobubble instability even under constant heating. Weak perturbations like sound wave can trigger new bubbles. Our findings open the possibility of using a nanobubble as an acoustic sensor or to enhance coupling to acoustic waves in photoacoustic microscopy. Thanks for watching.